Hess's law of heat summation. So this is next topic we're going to look at. So sometimes we want to find the enthalpy of reaction, but we can't do it in an experiment. Now this could be due to we don't have the right equipment, or there's a safety issue, or perhaps it takes too long for the reaction to actually take place. So we can still figure out what the enthalpy change will be, because if you can break down a reaction into steps, the enthalpy change for the net reaction, the overall reaction, will be the sum of the enthalpies for each one of the steps. So remember, enthalpy is a state function. How you get to the answer is irrelevant. The answer will be the same. So if you had two students, you had student A and student B, and they both needed to get to a spot in the classroom. Let's say these are desks. They both need to get over here. If student B did a whole loop-de-loop to get there, and student A took a more direct route, climbed over any desk that was in his way, the enthalpy change for both of them would be the same. It doesn't matter the path that they took to get there. The enthalpy change to get from point A to point B is the same. That's what a state function means. So with Hess's law, you must be given some information to start with. So you either have to have the chemical equation for the overall reactions, or you have to have the information so you can write it out. So you have the target reaction. And then the second piece of information that you have is the individual reactions that you're going to use to find the overall reaction by adding them up. Hence, law of heat summation, because we're adding the steps up. So we're going to do 4 different examples. First one, nitrogen monoxide can be formed from nitrogen gas and oxygen gas. What is the enthalpy change for the reaction? So here, the overall reaction that we're looking for is here in bold. This is what we want to find the enthalpy change for. We have been given 2 different chemical equations. Actually, they're thermochemical equations because we have the energy terms. So what we have to do is manipulate these so that when we add them together, we get the overall reaction. So start with one entity in this overall equation that's rather unique. So let's start with nitrogen monoxide. Which one of these 2 equations has nitrogen monoxide in it? So if you look in the first one, nitrogen, oxygen, NO2, nope. Here it is right here in equation number 2. So now we've identified the chemical equation that has it in it. So then you ask, is it on the correct side? In equation 2, it's a reactant. But in the overall reaction, it's a product. So what we're going to have to do is we're going to have to get equation number 2 manipulated so that not only is the entity on the correct side, but it also has the correct coefficient. So what we're going to do with equation 2, and I like to write it out as 2 prime, is we are going to flip and we're going to multiply everything by 2 so that we get the correct coefficient. So if we flip this, we now have 2 NO2s, arrow, 2 NOs, and 2 times a half is 1. so an oxygen. What you do to the chemical equation, you also have to do to the enthalpy term. So we're going to times this by 2 and flip it. If we flip it, that means the opposite reaction is taking place, so the enthalpy change is in the sign. So it's going to be plus 56 times 2. So delta H will be 112 kilojoules now for equation number 2. So now we have NO on the correct side with the correct coefficient, but we need to get rid of oxygen on the right because there's no oxygen up here. So, and if you look here, we've got 2 NO2s on the left. We have no NO2s on the right or the left. So we're going to manipulate equation number 1. So if we take equation number 1 and multiply it by 2, that will give us 2 NO2s on the right, which when I say right, I mean right of the arrow. Give us the 2 NO2s on the right, and because there's 2 NO2s on the left, they will cancel. And that will also give us 1 N2, which is what we want, and we'll end up with 2 O2s. We will cancel because we'll have 2 on the left, 1 on the right. So let's write out equation number 1. So 1 prime. So we have N2, half times 2 is 1, plus 2 O2s goes to 2 NO2s. And we have to take our delta H and also multiply it by 2. So that's 68 kilojoules. All right, so now do our summation part. If you line up your arrows, you can just basically cancel items that are on the left and the right here. Or you can write everything out and then cross it off. This first one I'm going to write everything out so you see more clearly. So we've got 2 NO2s and 2 O2s going to 2 NO, O2, and 2 NO2s. So you're adding up all your reactants, all your products, separating them with an arrow. And now we're going to cancel anything that's on the left side and the right side. So 2 NO2s and O2, 1 O2 from 2 O2s leaves me 1. So the overall equation, N2 plus O2 makes 2 NO gas. And our delta H will be, again, summation. We're adding these. So our delta H for this reaction is 112 plus 68, so 180 kilojoules. So that's how you figure out the overall answer. You manipulate the thermochemical equations to give you the correct coefficient and the correct side for each entity, and then you cancel out items that are on both a reactant and product side. Okay, example number 2. Iron can be purified from the single displacement reaction of aluminum and iron 3 oxide. So here is our overall equation. And we have 2 thermochemical equations to manipulate. So let's find something that's unusual in one of these reactions. O2 would not be something you would pick because it's in both equation 1 and 2. So let's pick Fe2O3, iron 3 oxide. Is it on the correct side of the arrow? No. It's a product. We want it to be a reactant. Is the coefficient correct? They're both 1, so yes. All we have to do is flip equation number 2. So Fe2O3 goes to 2Fe and 3/2 O2. So because this is the opposite reaction, the sign on our enthalpy change is opposite, but the energy change quantity is the same. All right, so that leaves equation number 1. Is aluminum on the correct side? So aluminum in equation 1 is on the left, and it has a coefficient of 2. Up here in the overall, coefficient of 2 and a reactant. So we can leave equation number 1 alone. I'm going to get rid of the second one because I'm going to work with 2'. All right, let's add these up. Now I'm going to show you the other way. Instead of writing out both the total reactants and the total products, I will cancel anything that is on both sides of these green arrows. So Fe2O3 occurs only once. So that's done. Aluminum, that only occurs once. So that's done. That only leaves 3/2 O2 as a reactant. I happen to have it on the right hand side as well. So it's gone. It gets canceled. So on the right hand side, I have Al2O3 and Fe. And if I double check up here, this is the same equation. My products are reversed, but that doesn't matter. 1 plus 2, 2 plus 1, same answer. All right, so now add up the 2 delta H's, and the value is -851.5 kilojoules. So to form iron metal from iron 3 oxide, 851.5 kilojoules of energy are released, because it's exothermic, per mole of iron 3 oxide reacted. Perfect. Okay, ethanol can be made industrially by the reaction of water with ethylene gas, C2H4. We don't have an overall reaction, but we do have enough information to write it out. So we know that water reacts with ethylene gas to produce ethanol. Okay, so let's double check that this is a balanced chemical equation. We have 2 carbons, 2 carbons, 2, 6 hydrogens, 5, 6 hydrogens, and 1 oxygen. So there's our overall equation, and we want to find the overall enthalpy change. All right, so first equation, C2H4 is on the left as a reactant, and in our overall, it is also on the left. So equation number 1 can stand. Equation number 2 has ethanol on the left as a reactant, but in our overall, it's a product. So we need to flip this equation. So 2' becomes 2 CO2s 3 waters goes to ethanol and 3 oxygens. And because we flipped it, it's the reverse reaction. The enthalpy change is now endothermic. Get rid of 2. I'm going to work with 2 prime. Okay. So let's take a look at this. Here's our arrow. On the left side, C2H4. It's only in one place. I've got 3 oxygens, and I have 3 oxygens, so they cancel. Then I've got 2 CO2s, they cancel. And then I've got 3 waters. And over here, I've got 2 waters. So 2 of them will cancel. And I'm left with 1 water. I have only 1 ethanol, and I have no other product. So there's our overall chemical equation. Now to make it thermochemical, I add up my delta H for each equation. So delta H is negative 44.0 kilojoules. So when ethanol is formed from ethylene gas and water, 44 kilojoules of energy are released per mole of ethanol formed. Okay, last example. How much energy can be obtained from the roasting of 50 grams of zinc sulfide ore? So this looks like it's a little bit more involved. Here we have her overall equation, and we have 3 thermochemical equations. So not only are we trying to find the enthalpy for the reaction, we also have to figure out how much energy is released when we have a certain amount of zinc sulfide. This equation that we're finding for will be for 1 mole, but this is not going to be 1 mole. 50 kilograms is not 1 mole of zinc sulfide. So first of all, let's get on with the thermochemical equations. Equation number 1 has zinc oxide in it. So find zinc oxide in the overall. So we've got zinc oxide, so it's over here. It's a product, coefficient's 1. It's a reactant, and the coefficient's 1. So we need to flip. So zinc plus 1/2 oxygen goes to zinc oxide, and our delta H will be negative 350.5 kilojoules. All right, next equation has SO2 in it, and it's the only equation that has SO2 in it. SO2 is a product, and it has a coefficient of 1. This also has a coefficient of 1 and is a product. So equation number 2 is going to stand. I'm going to get rid of equation 1. This is 1 prime. All right, equation number 3, zinc sulfide is on the left. In the overall, zinc sulfide is on the left. So coefficient's 1, coefficient's 1, so we're good. We can use equation number 3 as well. So let's add these 3 reactions up. So I'm just going to highlight so we can see the arrows. Arrow, arrow, arrow. Okay. On the left-hand side, starting with equation number 2, we've got sulfur. Sulfur is on the left in equation 2, but it's also on the right in equation 3. So that's going to cancel. We're going to come back to oxygen because it'll work itself out. We're going to look now at zinc sulfide. Zinc sulfide is only on the left once. It's not on the right at all. So we have zinc sulfide. Now, equation 1 prime, we have zinc here on the left, and we have it over here on the right. So that zinc is going to cancel. So basically what we have on the left is we have a half O2, and we have 1 O2. Another way to write 1 is 2 over 2. So if you have 2 over 2 and 1 over 2, we now have 3 halves of oxygens. We've got 1.5 oxygens. And on the right hand side, we have SO2 here. It's nowhere else. And so SO2. And we also have zinc oxide. We have zinc oxide here on the right, and it's nowhere else. So zinc oxide. So now we've got our overall equation. Gas, and a solid. So we're going to add up this delta H, and this delta H. So the overall enthalpy change is negative 441.3 kilojoules. So when zinc sulfide is roasted in oxygen atmosphere, we will release 441.3 kilojoules. Now don't forget, that's the enthalpy change for this reaction, so that's one step. You can get the molar enthalpy for this reaction from here, and we want to get it in reference to zinc sulfide, because it wants to know how much energy is released when you roast 50 kilograms of zinc sulfide. So we're interested in zinc sulfide. So if we make this a molar enthalpy, well, let's call it roast, is the enthalpy change for the reaction divided by the number of moles. So this is negative 441.3 kilojoules divided by 1 mole, because the coefficient in front of zinc is 1. There's 1 mole of zinc sulfide. Okay, so now we have some information. We have the overall reaction. From the overall reaction, we got the molar enthalpy. And once we have the molar enthalpy, we can figure out the delta H, the enthalpy change, for a specific number of moles. So delta H is N delta H roast. That's our molar enthalpy. So delta H is the number of moles. We've got 50 kilograms. So there's 1,000 grams in a kilogram. So we've got 50.0 times 10 to the 3 grams. That's not the proper way to write it, but that's how I wrote it. The molar mass of zinc sulfide is 97.48 grams per mole. And then the molar enthalpy is 441.3 kilojoules per mole. So our final answer is 5 to the exponent 4, so 50,000 grams divided by 97.48 grams per mole to give us the number of moles times 441.3 kilojoules. So our energy change is negative 226,354 kilojoules that is released. Okay, so negative 226,354 kilojoules of energy are released. Let's give this some significant digit adjustments. So minus 226 megajoules. There's 1,000 kilojoules in a megajoule. Or, if you want to stay in kilojoules, negative 2.26 times 10 to the 3 kilojoules. So in this case, we used Hess's law to figure out our enthalpy for the reaction. We had a specific quantity of a reactant, could be a product too, but we had a specific quantity of a reactant, so we could find the enthalpy change for that amount in the reaction. So once you found Hess's law, you could find the delta H, the enthalpy of reaction, which is what we found here. And then we found the number of moles we used. We multiplied that by the enthalpy change for 1 mole of zinc sulfide by bringing out the molar enthalpy from the thermochemical equation. And then we calculated the energy change. So quite a lot of energy is released when 50 kilograms of zinc sulfide are reacted.